All right, hello again. This is a lecture for July 13th, 2016. I'm recording this a day early on July 12th due to some scheduling issues. All right, so here we are once again. Let's see. As a reminder, we'll have homework due tonight. This will be the first homework assignment after the intro assignment that was due on the evening of the 12th. And so let's just get started. All right, let's see. We are recording and we're good to go. All right, so for the first part of the lecture, we're going to talk more and elaborate about the stress-strain curve that we discussed for the first time on the previous lecture. So let's see here. The first step is to look at, I want to expand upon the stress-strain curve that we've discussed previously. So let's see, on the stress-strain curve of various materials, again on the y-axis we are going to have the normal the normal stress, and on the x-axis we're going to have the normal strain. Oh, that looks terrible, man. I want to draw this a little bigger too. So on the y-axis we are going to have the normal stress, and on the x-axis we are going to have the normal strain, like shown. And you know what, I might even draw this a little bit bigger, just because this is, we're going to put a lot on here, and I really want to make sure we have enough room for everything. There we go, much better, pretty much the whole slide. Okay, so on this axis, of course, we're going to have sigma, which will be in KSI, or any unit with force over area. Sigma in KSI, and epsilon here, which is unitless. Or you can think of it as inches per inch, millimeters per millimeter, etc. Say inches per inch for simplicity. All right, and then we have a series of, well, we have our main curve that I'll draw. Here, like so. Then we have we go flat for a while. Then we have a line break. This is not, these lines themselves don't mean anything except the graph continues much further horizontal to the right than we might otherwise be able to show on this slide. With then the failure here. All right, so let's see. And this whole thing again is the normal stress, normal strain curve. The normal stress, normal strain curve. All right, so I am going to label a whole bunch of things on here. Well, let's see. First of all, we have the first thing to consider is the proportional limit, which we discussed last time a bit. And let me label some of these in blue. The proportional limit, again, is where the curve ceases its linear behavior. So this is going to be sigma PL, where sigma PL is the proportional limit. Let's see, what else do we have? Then sigma yield, let's see, proportional limit, here. This is going to be sigma y for sigma yield. Sigma y, Sigma y is going to be your yield limit, or sorry, your yield stress. This is the stress that yielding occurs at. The portion of the graph that is horizontal, here we refer to as yielding. Then, this stress at this local peak is the sigma EL, the elastic limit. Sigma EL. Sigma EL is the elastic limit. It is the limit at which the graph is no longer elastic. It is outside the elastic range. EL here. EL is the elastic limit. The elastic limit. Let's see, what other sigmas do we have? Well, we'll need the sigma ultimate. The stress here is the sigma ultimate. Sigma ultimate is, as it's described, it is the ultimate stress that the material can ever withstand. And it's only after a long range of yielding that this happens. So this is the most you will ever get out of the sample of material. This is in a, this is past the point of yielding. It is now completely finished. This is the maximum load you will ever get this thing to carry. And even then, it's to that point, it's permanently deformed. Let's see. And then finally, this stress here, if I carried this all the way across, in fact, let me just go ahead and do that. Let me trim that a little bit, erase that. I don't necessarily like the way that turned out. Here, this is the sigma R, which is the rupture stress. This is the ultimate stress, and let's see that this is the rupture stress. This is well below the ultimate stress, but this is the stress that the material actually physically breaks apart at. Okay. So a few things. Let's see. What else do we need to consider? Now, let me label some things in some zones in purple. First of all, we have two broad regions of the graph. The elastic and the inelastic. This is the elastic region, here to here, the elastic region. Everything beyond is the plastic region, or the inelastic region. Inelastic or plastic region. The inelastic or plastic region. So it is not linear for the entire elastic range, but what's happening fundamentally is what separates the elastic from the inelastic zone is that in the elastic zone, all of the material in a section is under the elastic limit. When the outer fiber reaches the elastic limit, that's when you have that's when you're leaving the elastic zone and entering the inelastic zone. Also, more critically, this represents reversible deformation. You can load this up until this point, and when you unload it, it will spring back to the point to the original shape prior to loading. But after this point, after the elastic limit, it will no longer, after this elastic limit here, it will no longer be able to do that. In fact, it will instead result in permanent deformation. If you think of like a, I don't know how many of you had, say, a Slinky when you were a child, or maybe some other spring-based toy, and children, they'll find when they're playing with those, they love stretching them out and compressing them, stretching them, compressing them. They inevitably end up bring them too far. And they will discover that past a certain point, you can stretch it past a certain point, but then it will no longer spring back. And that's because you can stretch a slinky or any spring up until a certain point, and as long as it's not past that certain point, it will still be in the elastic zone. But beyond that zone, it will be undergoing plastic deformation. It will be undergoing permanent deformation, and it will actually represent a loss of energy from the system, and it will have to, the only way to make it go back is to input energy. But in other words, this is permanent deformation. Okay, some other regions of this curve that you may have or may not have heard of. We call this region of the curve, the horizontal portion here, yielding. Call this portion of the curve yielding. From here to here, the part of the curve where the graph is horizontal, yielding. And we'll discuss what this means when we get to beam theory in relation to yield stress through a section, or stress through a section. Now, you do get a little more stress towards the end, basically right before the ultimate stress. This is your strain hardening region. Strain hardening. And the book will go into this in more detail. You gain a little bit extra stress from the stress that's already there. This is strain hardening. On very large deformations, very large strains, you can get a little bit extra stress here, and that's what allows you to get that peak at the ultimate stress. And this is higher than this. This is truly this peak here is higher than this generally. This really is the ultimate stress of the material. And then here, finally, we have the final region where the material is just giving up altogether. This is where the material is rapidly thinning, happens relatively quickly. This is the necking region, where your sample is rapidly thinning before it just snaps altogether like a piece of silly putty breaking in two. Okay, let's see. So I will define some more of these a bit later on the next slide. Now, let's see. I do need to define something, so I need to list some other things on here, sorry. So, as a reminder, the Young's modulus, or the elastic modulus, is going to be the slope of the linear portion here, 1 in E. However, we need a way of estimating this. And the problem with estimating the Young's modulus from the slope of this line is that it's often kind of vague exactly where this curve stops being linear. Do you estimate it from here and project it downward here? Do you estimate it from here, project it downward? It's kind of hard to show on a hand graph like this. But generally, it can be hard to estimate exactly where the curve stops being linear. So that's why we usually use something called the 0.02% offset method. When we're trying to estimate the modulus of elasticity of a material. So instead of trying to directly estimate the slope of this curve here, instead we go to the yield stress, and we project a line downward from there to a point of 0.002 strain, or 0.2%, or 0.2%. This is known as the 0.2% offset method. So essentially you would have this, how you'd find the slope of that? Well, you have this ordered pair, this strain and this yield stress, that's one ordered pair. Your other ordered pair is going to be 0.002, 0. So 0.002 for the strain and 0 for the stress, and then you just find the line between 2 points using the technique you've learned in Algebra 1. And the slope of that line is going to be your yield stress. So that is the 0.02, sorry, that's the 0.2% offset method. All right, let's see. And I alluded to this here in that if I should mention again the concept of permanent set, which is if you are in this range, you are past the point where things will spring back. So if you were to release the stress, if you were to release the load here, what would happen is it wouldn't go back and spring back. It would not go back all the way and go back up over the curve and come down again. It will actually follow an elastic behavior and end up about here. So if you release the stress here, it will follow its elastic modulus down and end up at a deformation here. This becomes essentially its new undeformed shape, its unloaded shape. So when you're in the yielding zone, you have now resulted in permanent deformation. All right. And again, it would be good to remind us that epsilon is equal to delta L over L naught, if we've forgotten that. It's equal to the change in L over the change in length over the original length. All right, so study that. Now, there are a few other terms that we should be aware of. Terms to know. Terms to know. Let me make sure we're still recording here. Okay, we are, so let's keep going. Okay, so terms to know. Well, the first one is going to be yielding. I mentioned it briefly, but I think I'll actually write out what this means. Yielding. I'll also formally define strain hardening and necking. Strain hardening, that's a mutated E there if you can't read my terrible handwriting. Necking, and let's see, true versus engineering strain. I should probably elucidate on that too. Versus engineering strain. Okay, so what do we mean by yielding? That's in the yielding zone. It's in the plastic or inelastic range. And what do we mean by that? Let's see. So during yielding, molecules realign. There is slippage of material along oblique surfaces. So material is slipping along oblique surfaces. There's going to be permanent deformation of material along oblique surfaces. All right, let's see. In other words, it represents a relationship with shear stress or release of shear stress. Okay, strain hardening is the realignment is complete. So in other words, what do I mean by this? Materials are usually slightly stronger in one direction or another. And so during yielding, you're having a realignment of materials such that you're seeing a realignment of the actual crystalline structure of the material such that that it can more effectively resist load. But when the point of strain hardening, the realignment is now complete, and after that's completed, you have now maximized the stress you'll get out of this. And necking is local instability. So what happens is the material starts rapidly thinning, and as the material thins, as the cross section thins, as it thins, that then thus increases the stress because there's less surface area as in the cross section, so that makes the stress go even higher, which means it thins even more, and the thing quickly just essentially collapses or pulls apart, I should say. Okay, true versus engineering strain. Engineering strain, we define epsilon as the change in length, delta, over the initial length. The true is delta over L. And this may seem like this is sort of a scientific definition. Epsilon equals delta over L. But what's the difference? Well, let's see. This would be the true, true versus engineering. How do we distinguish this? What is the difference between L and L naught, essentially? Well, I would say the difference is L naught is what we actually measure. That is something we can actually physically measure. However, the true scientific definition of strain would, of strain, would say that the L would actually be the completely unloaded, absolutely zero ideal length L. If this thing is completely unloaded at all. However, that is nearly impossible to create. Often sometimes there is initial deformation or initial stress in a material just from its own manufacture. Sometimes when, say, steel cools, after it is formed, it results in a certain amount of locked-in stress actually built up within the material. Or sometimes, or if we really wanted to get pedantic, we could start arguing that there is some built-in deformation just resulting from the material's self-weight under gravity that is always going to be there. So usually, though, that is minor enough that we can simply say, okay, we don't need to worry about that. We'll just treat L as the initial L naught that we happen to measure. We'll consider all deformations prior to our initial amount as unimportant. All right, so finally, let us compare some terms and material properties. So I'm going to define a series of properties, and in layman's terms, these are all used interchangeably. However, in engineering, these terms are not the same. They have very specific definitions that are unique to each other, or unique to themselves. So let us compare terms and properties. The first four of these, in layman's terms, are all the same. Terms and properties of materials. Terms/properties of materials. All right, so the first one is stiffness. What do we mean by that? What do we mean by stiffness? Well, stiffness. Well, stiffness is given by the letter E, of course, the modulus of elasticity. This is the E found on the curve. What do we mean by this? Stiffness, fundamentally, is the ability to accept large elastic loads with little deformation. The ability to absorb large elastic loads with little deformation. Loads with little deformation. That is fundamentally what defines stiffness. A stiff material is one that can absorb a large load without deflecting that much, or without deforming or stretching or bending or twisting, or whatever you define it as. And that is given by the slope of the linear portion of the stress-strain curve. Okay, what do we mean by strength? Let me write this in maybe red. I think I like that better, just to make it stand out. In red, I will write the appropriate variable, or where you find it on the graph. So in fact, maybe I'll just write all of these out really quickly. Then let's look at strength, and we'll define exactly what we mean by strength. Strength, toughness, and resilience. And we have a few more of these to define, but I won't, I'll list those later. strengths. I just want to focus on these four first, because all of these, at least in terms of layman, at least in layman's terms, are the same thing. If you ask the average person talking about, say, the strength of a beam or something, or a column, they'll say stiffness. If they know what a column or a beam is, they'll tell you that strength, stiffness, toughness, and resilience are really all the same thing. Sometimes you see these referred to, say, the exception being if you're referring to, say, I don't know, properties of a human being or something, and then they'll talk. This would be, maybe some of these would be like a personality trait or something. I don't know. But in terms of engineering, each of these has very specific definitions, and we are engineers here, or aspiring engineers, so we want to use the proper um, formal definitions, proper technical definitions. Okay, strength. What do you mean by strength? Well, sigma ultimate. Strength is the ability to accept large loads without rupture. In other words, sigma ultimate is the max stress, so the ability to accept large loads without rupture. So the greater the max stress, the greater the ultimate stress, the greater the strength, the stronger the material. The ability to accept large loads without rupture. Okay, so what do we mean by toughness? Well, toughness is the ability to measure, or to not measure, the ability to absorb elastic and plastic energy before rupture. Large amounts of plastic and elastic energy before rupture. Elastic and plastic energy before rupture. Before rupture. And it is given by not just total area, we mean the total area under sigma epsilon curve. So the more area you have under the stress strain curve, the tougher the material. Because this sort of, if on the stress strain curve, the integral, the area underneath it, represents energy. It's directly proportional to energy. So if you have a large area under this curve for material, it means each square inch of material can absorb quite a bit of energy before it finally ruptures. And resilience is like toughness, except it's limited to the elastic area under the curve. This is under the entire stress strain curve. This is the area under the elastic portion. Sigma epsilon curve. And resilience fundamentally is the ability to absorb elastic energy. So you want to be able to absorb a large amount of energy without having permanent deformation. So in other words, a very resilient slinky would be one that could absorb a large amount of force or energy without being permanently deformed. The ability to absorb elastic energy. A very unresilient material would enter its plastic range relatively quickly after just a very small amount of force. Finally, ductility. Ductility. What do we mean by ductility? Well, first of all, it is designated by a large rupture strain of rupture. Large epsilon r. Did I indicate that here? No, I didn't. Sort of. Let me show you that here. This here in orange, if this is the rupture, if this here is the rupture stress, this here would be the rupture strain, epsilon r. So a very large epsilon strain means indicates a very ductile material. It doesn't mean that it has to have a large a large sigma r, a large rupture stress, it simply means that it can deform a great deal prior to rupturing. If you think of a very if you think of a very ductile material, it can bend, it can undergo large deformations before it actually ruptures. So I like to give the example when I define ductility to certain students that if I go up to the hood of your car and wail on it with a hammer, it will dent. Now you'll be very mad at me if I do that, but it will dent rather than break. If if the hood of your car are made of something, say, very brittle, say glass, I don't know why you'd make the hood of your car out of glass, but maybe for some strange reason you want to see your engine as it runs, you could make it out of glass for some insane reason. But unfortunately, if you had the glass hood of your car and I go over to hit it with a hammer, it will shatter into a million pieces because it cannot absorb a large amount of strain before rupturing. So again, ductility is the ability to deform before rupture rupture characterized by a large plastic strain, by a large plastic region. By a large, and I have one more term that I'll have to put on the next slide, plastic region. And the opposite of ductility, of course, is brittleness. So let me put a title on this. Terms continued. The opposite of this, of course, is the opposite of ductility, of course, is brittleness. And it is also indicated by epsilon r. It is also indicated by an epsilon r, except it's indicated by a small epsilon r. This is indicated by a large epsilon r. This one is indicated by a small epsilon r. So a brittle material breaks or ruptures with without large deformations, with very small deformations, And this is the opposite of ductility. The inability to deform before rupture has characterized by a small plastic region. By a small plastic region. And let's see, by a small plastic region. And I think that's about it for this portion of the lecture. I just wanted to go over a lot of material properties. I wanted to really go into great detail. Like I promised earlier, I said we were going to go in greater detail into the stress strain diagram, and we have. So this first portion of the lecture, we're just going to focus on going over the stress strain diagram and really focusing on the different material properties and exactly what these mean. Again, you need to be very familiar with the stress strain diagram. You need to know what each of these regions is. You need to know what each of these quantities is. So please read about this in your book, go over the lecture again, and really be familiar with all of this material and all of these terms. These are basic, fundamental engineering terms. And yes, while these four quantities are used interchangeably in common parlance, stiffness, strength, toughness, and resilience are four very different things when it comes to actual technical classification. All right, that will do it for now, and I think I will see you quickly for the next portion of the lecture.